Greetings, students. In this series of videos, we are going to be looking at using definite integrals to find volumes of revolution. So I know it's taken us a while to get here, but I wanted to get to this lesson because several of you are doing this for your IA topics. So first thing I want to do is, these are just sort of general instructions, and we'll be applying those to the problems that we're going to go through. But I just want to give you a general idea of what all of this is talking about as far as finding volume. So I'm going to go down here to this blank space that's at the bottom and just kind of talk you through it. So what we're going to be doing here, I'm not doing this for any particular function, I'm just kind of showing you a picture, is let's suppose that we have a function like this, and that we want to take the region that's between here and here. All right, so this whole region that's in here, and we want to revolve that or rotate it around. I'm going to get rid of these little marks here. Rotate it around the x-axis. All right, so I want you to imagine just taking this like a piece of cardboard that's cut in this shape. It's stuck onto the x-axis, and we're just going to twirl the x-axis. And so when we do that, this object is going to come up out of the paper. It's going to rotate 180 degrees around, and then eventually in its rotation, it's going to land over here, right? And then it's going to continue rounding or revolving around back behind the board and then coming back to where it was. So if I imagine a point like this in the rotation, you should be able to imagine, the problem is like you can't see my 3D movements here. It's going to, again, come up out of the board in a circular shape and then land back here and then continue its circle on the other side. So if I was going to kind of try to draw a 3D, it would look like this. Right? And then, normally we make little cuts. If I'm finding area, I would make little cuts in different places. So if I imagine all those little cuts, all of those would lead to another little circular piece like this. All right, and then this down here would be a circle. So we'd have all these little circular pieces. All right, but if I'm cutting it like this, then you should be able to imagine this piece right here that I just cut out as being almost a flat cylinder, because it has a circular base like this and then just a little tiny height. So it's going to look like that. Okay, now I know you might say, well, it's not straight here, but what we can do is, just like we did with area, just kind of pick a point here and make a vertical piece, well, horizontal in this case, make a horizontal piece to make those straight, right? And then there's what we're going to call our sample disc or sample cylinder. So just like when we did area, we had a sample rectangle and we found the area of that sample rectangle. What we're going to do is we're going to find the volume, because we're looking for volume here, of this sample cylinder or sample disc. So we're going to find dV. So if we think about the volume of a cylinder is pi r squared h. Pi r squared because that's the area of the base. And then we take that base times its height, and that gives us the volume. So in this particular picture then, our cylinder, of course, is sort of this way. And so the radius would go from here up to here. So that would be a radius of our cylinder. And then the height of the cylinder is going to be dx, because I'm making these cuts, every dx units. And then remember again that the idea is that we're going to take the volumes of all of these cylinders, infinitely many cylinders, we're going to add them up, and we're going to let the width or the height go to 0. And that's going to turn this into the exact area. So our dV then is going to be pi times, now we need to figure out what the radius is. So the radius is the distance from here to here. So if we think about what a couple of those points are going to look like, this point right here, which is on the x-axis, and this point right here, which is on the curve, are going to have the same x-coordinate. So this is going to be x something. This point, because it's on the y-axis, is going to be x0, and then this one's going to be xy. All right, so whatever our function is, y equals f of x is our function. So then that means that this radius is going to be the distance, which is y minus 0, all right, bottom or top minus bottom. So y minus 0 is just going to be y, but we want the radius squared times the height, which is going to be dx. So that's the volume of our sample. Then if we want the volume of the entire figure, then what we're going to do, as we said, is take all of these cylinders, add them all up, let the width go to 0. And what that process is finding an integral. So we're going to do the integral from, in this case, we're making the cuts here starting at 0 all the way up to, I didn't give this a number, let's suppose that it's 6. We're going to make these cuts all the way from 0 to 6 of this. This becomes the integrand, pi y squared dx. And that's our total volume. Now we do want, as before, technically we want the x and this to be in terms of the same variable, to be in terms of x. When we did area, I let you kind of leave this in here because you were going to use your calculator to do the integral. But as we go through some of the examples here, I'll actually kind of substitute that in just to show you what it will look like if you're going to have to do it by hand, for instance. All right, so if we go back and take a look at the steps that are here, as far as what it says anytime you're finding a volume of revolution, right? Volume of revolution, because we're revolving this region around an axis, either the x-axis or possibly the y-axis. So you're going to have to sketch the graph, find the coordinates of the points of intersection. So just like you did when you did area, try to sketch the solid of revolution. I know not all of us are artists, but we can try to do something. All right, then it says we have to decide whether we're going to cut it into horizontal or vertical strips. Are we going to cut it into strips of width dx, which is what you would do if you're cutting it this way? Or are you going to cut it into strips of width dy, which is what you'd do if you cut it this way? With volume, we don't have as much choice. With volume, the strips, the way you're going to cut them are always perpendicular to the axis of rotation. So if you're rotating around the x-axis, then you must make vertical strips. If you're rotating around the y-axis, then you must make horizontal strips. So you don't have a choice, really. So as it says, as you're rotating around the x-axis, you're going to make horizontal cuts. Sorry, vertical cuts, I just said this. And if you're rotating around the y-axis, then you're going to make horizontal cuts. Okay? All right, then the next step, it says find the radius and the height of the sampled discs, which is what we did. And just like before, you want to keep all values positive because you're doing geometric volume here. And this just talks about if your region is bounded by two different functions, what you have to do. And we'll see an example of that. All right, then you're going to find the formula for dV, the volume of the sample disk. We did that just a minute ago. And then that becomes the integrand for your integral. Then you set up the integral and you evaluate. All right, so I'm going to stop here and we will do the first example.